Well, thank you very much for this introduction. So we'd like to thank the organizers for this great conference and for giving a chance to present this lecture here. So what I want to do with this lecture is to show to use renormalization via conjugate fractions to construct infinite worlds, symbolic, dynamical systems with some prescribed regularity. And I want also to convince you that for some extra regularity, like multi-scale regularity, like described by John Smiley yesterday, we even need renormalization. So I'm mentioning regularity. I will start with some very concrete example coming from social sciences and scheduling theory. So I will use it as a toy situation, as a warm-up, and then we will increase the level of requirement for regularity for subshifts that we want to consider. So I start with this, yeah, thank you very much, then you see better the choice of colors and stuff like that. Thanks. So we start with this problem, and there is quite a large literature, in fact, on this kind of assignment problems in social sciences for this kind of electoral context. So we are given K-states, they form a union, we want to find some chairperson, and we want to make it in a fair way, fair meaning that if you look at some time, the accumulated number of chairpersons from each state has to be proportional to the weight of the state. So say like that, you could say, okay, it's something related to some rational data, but for the weight, we can take something which is not necessarily the ratio of the number of inhabitants of a state with respect to the total number. For instance, in the EU, they take a square root of number of the population. So that doesn't mean that we need to have rational instances. And in fact, we will work with irrational instances in all this lecture to have a dynamical viewpoint. But I really stress the fact that there is a huge amount of literature on this kind of a problem. So for the moment, we can formalize this in terms of, let's say, word combinatorics for the moment. So given some prescribed vector of frequencies for the letters, we want to find infinite words, sequences, with values in a finite alphabet, the number of colors we consider. We want to have prescribed frequencies. So the frequency is defined as the number of times you will find some letter, some color in a prefix of length n divided by this length if this limit exists. And in fact, it's not difficult to see that it's not only a question of frequency that we are considering, it's a question of discrepancy. Symbolic discrepancy in the same way as natural theory of discrepancy in number theory. Look at the number of times you visit some interval, say, minus what you expect. So that's the same notion here for infinite words. You're in fact not measuring not looking only at the frequency, you want to compare the number of times you find a letter in a prefix minus the expected value, that is to say, the length of the prefix times the expected frequency. So you want to find assignments, infinite words, which have at least a bounded discrepancy and, to be fair, the smallest discrepancy. So for the moment, it's completely static. I mean, it's combinatorial. And that's nothing to do with renormalization dynamics. So let's continue to try to reformulate this in more dynamical terms, more geometric terms. So just to represent things, if we plot in this diagram the number of times we find each of the colors, and if we compare with the expected values on each of the diagrams, I take a line with slope directed by the 3 possible frequencies. If we plot here the histograms of corresponding to the number of choices we made for each of the states, each of the colors, we want to have lines which are not far from discrete lines, broken lines, which are not far from the real line directed by the frequency. Okay, so that's what we want to do geometrically. So if you see it in 3D, instead of having these 3 diagrams, take a line directed by my 3 frequencies, my vector alpha, and you want to find infinite words. that you represent in 3D by associated with each letter one vector of the canonical basis. So you follow your word as we did here, but directly now in 3D by associated with each of these colors one vector. You get a broken line, and you want this broken line, this line with integer vertices, to be close to some line. So that's what it means to have bounded discrepancy. Okay, so that's the picture that you will find on the right. You want to create such words. So the question of having infinite words with a small discrepancy dates back to the 60s. With no surprise, people like Niederreiter, Tiedemann, who investigated this question of equidistribution for discrete sets. And then Niederreiter asked first the question, is it possible to find an infinite word creating something with bounded discrepancy and even discrepancy smaller than 1 for any kind of alphabet and any kind of vector frequencies? So to have something bounded, okay, you have just to follow the line as you see here. To have something smaller than 1 requires a bit of thinking. And then Meyer and Tiedemann considered the following question, trying to find the best bound in the following sense. You fix alpha, your letter frequencies vector. Then you want to find the best candidate, the sequence having this given alpha, which gives you the smallest frequency. And then you want to have something independent on alpha to see what is the worst situation for the best case. With respect to alpha, you take the supremum over alpha. So in the 70s, they arrived to the fact that we can realize something like 1 minus 1 over 2d minus 2, where d is the cardinality of the alphabet. Okay, so we're like that in the 70s. Then the question is, what can we say about these words? How can we make it effective? All kinds of questions we can ask. And so as a warm-up, let's take the case d equal 2. So d equal 2, we find 1 minus 1/4, so 1/2 as a discrepancy. So then what could be candidates for infinite words who have a small discrepancy? Well, here. Thank you very much. Okay, Sturmian words, no surprise. Okay, so in fact, Sturmian sequences correspond to the best candidates for this kind of situation. So you are no completely expert in Sturmian sequences because thanks to John Smiley's lecture, you know what are eating trajectories for square billiard trajectories. So another way of looking at the dynamical systems is to say that you code orbits of a translation mode 1 with respect to 2 intervals. You couldn't make more simple as a coding because coding with respect to 1 interval would give constant sequences. Take 2 intervals. Then you have 1 parameter for your rotation, alpha. It's the simplest coding you can have is not to introduce some extra parameter. So the best situation is to take something already related to alpha. Okay, so we take 2 intervals. Both intervals has length alpha, and we code orbits. So we follow the orbits starting from x, and then we code the orbits with respect to the intervals you visit. So you associate with this geometric dynamical system, words, infinite words, a shift, a subshift, a set of infinite sequences endowed with the dynamics of the shift that just suppresses the first element of a sequence. And in fact, you have the nice property that you don't lose that much information in the sense that you have an isomorphism between the 2 dynamics, the geometric one and the symbolic one. You have an isomorphism in measure, of course, it cannot be topological. And then you've seen this yesterday, you have a nice renormalization through continued fractions that describe Sturmian sequences. So that's a kind of ideal situation where the solution to the combinatorial problem is as a dynamical geometric flavor and gives a lot of information, and you have even more than that. Because you could ask, by the way, why do we have bounded discrepancy or even frequencies for letters? Well, it's just a question of uniform distribution. By unique ergodicity of your Thoreau translation, if alpha is irrational, well, you know that frequencies exist correspond to the length of intervals. discrepancy, it's a bit more demanding. Why do we have bounded discrepancy? Why is it that the time spent in one interval minus n time main expected value is bounded? Comes from a theorem of Kesten that says that as soon as you have length which are in alpha z plus z, which are related to z mod 1, then the discrepancy is bounded. Okay. So that's true for letters. But now we have this multi-scale phenomenon I want to stress here. That is to say, if you look not only at letters but at factors, so by factors I mean subwords here. 1 is not factor. I want two letters to occur consecutively. So if you look at factors, with this dynamical model, well, we have all the machinery that we can need. We just refine the partition with respect to the dynamics. So if you want to see whether you see the factor 0, 0, you refine the interval I0 with respect to the dynamics. So in other words, if you want to see whether you see 2, 0 in a row, you have to be in the interval I0 between 0 and 1 minus alpha. And suppose alpha is smaller than 1/2. If you want to see again a 0, you have to be at the beginning of the interval between 0, 1 minus 2 alpha. You refine your partition and then you associate with each of the three words you see one interval. Okay, that gives you 3 factors of length 2, and in general, with the same reasoning just given for free by the dynamical viewpoint, the number of configurations, factors of length n, corresponds to the intervals you get by refining the partition with respect to the dynamics. Well, you plot the point minus k alpha mod 1, from k running to 0, 0 to n, you have n plus 1 points, n plus 1 intervals because we are mod 1. Okay, so that's also a nice property information that we have on Sturmian sequences, which is, by the way, also like a little miracle for 2 letters, which says that this is even a characterization of Sturmian words. And then by uniform distribution and the argument we've seen with Kesten, we have existence of frequencies, bounded discrepancy. Okay, that's the situation for Sturmian words. We have a small number of factors, we have renormalization, we have bounded discrepancy, and even the smallest discrepancy. And also, just to have a flavor of the renormalization, if we take some particular alpha, say the golden ratio, then we can use the fact that alpha is quadratic. We can use the self-similarity, which is beyond the fact that it's quadratic, to translate it into a so-called substitution, like an induction step in some renormalization process. So with a golden ratio comes the ubiquitous Fibonacci substitution, which replaces letters by words that you can iterate, so that it creates infinite words. These infinite words are such that the dynamics which is behind is minimal, uniquely ergodic, and then you create, with this kind of symbolic method, a coding which corresponds to what we've seen before, but it's completely symbolic here, and you get, once again, a symbolic coding of the golden ratio translation. What we have used here is that the golden ratio is algebraic self-similar. It goes with the matrix 1, 1, 1, 0, which has the golden ratio as eigen element, as eigen vector, eigen value, merci. And then, and also we have this correspondence between a substitution and a matrix. I put in columns the number of occurrences of the letters in this symbolic rule. So starting from alpha, I have a matrix which is natural with alpha. I make it combinatorial, I create a rule, and then I arrive to, again, one particular instance of a Sturmian word. So we have in the 2-letter case a lot of tools at hand. I really stress the case that it's like one step of induction. So if your favorite model is Rosy induction and interval exchanges, we are really doing the same, except that here we have always the same step. So it's like a step of Rosy induction if you think in terms of interval exchanges. Okay, so that's a nice situation we have for 2 letters. So we started with a problem completely combinatorial, and we arrived to a nice dynamical world of solutions. But Of course, the question is whether it's related to the fact that we have two letters, and the question is what happens for higher dimension alphabet. So we have two options now. We can either try to invent different sequences or try to test what we know, which generalized Stumian sequences, to see whether they fit with this regularity question we ask about discrepancy. So let's go for the generalization of Stumian sequences. So Stumian sequences code two rotations. Rotations are two interval exchange maps. Okay, so let's go for three interval exchange maps. So are we going to create infinite words which have this regularity defined like bounded discrepancy? Well, no, we know that it won't work because of the behavior of Lyapunov exponent. So the discrepancy is not bounded. You have deviations. If you count the number of visits you have with one interval under the action of an interval exchange, if you compare it with the expected value. Okay, so we won't go in the direction of coding of interval exchanges. So now we can use the idea that Stumian sequences code trajectories in square billiards to go to the hypercubic billiard case. We will try this. We can keep in mind this idea that we have used a rule like Fibonacci, a substitution. What was important in this substitution case, it's a so-called Piso case. This substitution, we have seen that it came with a matrix. This matrix, when you iterated with Perron-Frobenius, you can understand the behavior of the dynamics which is behind, and to understand the behavior of powers of matrices, you look at the eigenvalues of this matrix. So a Piso substitution is a substitution for which the characteristic polynomial of the matrix which goes with the substitution is a minimal polynomial of a Piso number, which is an integer, an algebraic integer, which has the roots of its minimal polynomials are all of modulus smaller than 1. You have only one root larger than 1. Okay, so we could use that, and you could also try to code translations in the d-dimensional torus. So that's what we are going to do in this lecture. So we have seen that coding of interval exchanges won't do the job. So we will explore the cubic billiard trajectories, and then for the normalization we will use Piso substitutions, and we will stick to codings of translations. So what we will do now is to try to test the idea that if you give me this problem of chair-person assignment, it's a reasonable way to try to get solutions to this problem in terms of codings of a simple dynamical system, a translation of the torus. There is no simpler dynamical system, which is infinite. You add something mod 1, and let's suppose it's minimal. Let's take alpha, a vector which has rationally independent coordinates. That was my comment from the beginning, that we would work with frequencies that would not be rational. Okay, so we start with such a minimal translation. And also, why are we working in d-1? So d, my number of states, my number of colors. I start with the frequency vector. The frequencies, the coordinates add to 1. So in fact, my problem is d-1 as d-1 parameter. So it's not a surprise to work on d-1. We started with the Stumian sequences on 2 letters, but which describe a one-dimensional dynamics. Okay, so I want to test the idea. Is there a relation between the discrepancy problem and translations? So, okay, so we did the Stumian case, so now let's go to the cubic case. So, Stumian case, another way of looking at them is cutting words, hitting trajectories, with a picture in the middle, which correspond also to a trajectory. I use this picture to illustrate that the fact that the dynamics, the mod 1 dynamics, is transverse. It's in the blue line that you close, and then that gives you information on the dynamics. This is the mode 1, which is here, and which tells you which color you will meet in your heating trajectory, or when you unfold it, what you will cross. So that's the situation for 2 letters. Okay, let's go for the billiard world. Okay, so we travel along a half line. We are in hypercubic grid. So let's say in Z3 we meet cubes, we meet faces of cubes, and we have to code this. So that's exactly the same, but with, let's say, 1 dimension more. So we have a natural convention. If we hit a face orthogonal to some vector ej, well, we use the coding j. So by coding a trajectory, as you saw in the previous slide, okay, you get infinite worlds. So now the little gym to do now is to recognize from this picture the total translation. So what I depicted here is the cube that you take to select points. So you travel along a line, you meet faces of hypercubes. If we take the vocabulary of cut and project schemes that you saw with the lecture VNs, what you're doing here is that you are sliding a cube along a line, and you have this window as a selection window. Here I depicted the hypercube projected along the line that I am following. I am traveling along this line directed by the vector alpha, my vector of letter frequencies. Okay, project the cube on the anti-diagonal plane. And then I've got the picture on the left. But I've got 2 ways of looking at a cube. I can look at it from above, from below. So I've got 2 projections. Now, if I live in the plane with orthogonal vector 1, the anti-diagonal plane, I can tile with either of these pictures. So what I claim is that this exchange of pieces is, in fact, a translation by alpha mod 1, because I tile periodically. So it's just a visual way, a visualization of a translation mod 1. A 2-dimensional translation on the 2-dimensional torus. So it's just a way of visualization. And then these hypercubic billiard worlds have been widely studied. And for instance, you have work from Arnaud Mauduit, Yokohama, Tamura, Baryshnikov, Bédari, Dubert, who looked at their, for instance, their factor complexity. Okay, are these worlds good candidates? Ouais. The picture, because I projected it along a line of vector alpha and on something transverse. So the projection of my cube has made this deformation. So you see a cube that is deformé. What is the, sorry? Exactly, 2 projections, and then you can project either the lower cube or the upper cube. In 2D, you would, if you see 3D, yeah, exactly. So I will do it in 2D first, and then, so in 2D, a square, you can either project the upper square, the lower square. And then when you project, you will deform. Okay, so okay, so you have this, a lot of squares. You need squares, and then you have a line, and you want to project along this line on the line which is vector normal 1. And this is why that makes this deformation, and when you project, you won't have 2 intervals of the same length. And according to the fact that you project this, you will have these 2 intervals. And if you project this, you will have 2 other intervals, and that's nothing else than exchange of 2 pieces and a rotation. Thank you for asking. So it's just visualization of what is a rotation. So now, if you think of the first pictures, representations, geometric pictures we had, we select points by sliding some bounded window, like in a cut and project scheme, and we select points. They are all within bounded distance of my frequency line, so they are a bounded discrepancy. Okay, so now we have, like in the Schumann case, the nice property that we have infinite words with a dynamical system. We can compute a lot of stuff like we did for Schumann case because we have a rotation at hand. We have a coding with respect to this visualization of the rotation. And then the question will be, how good is the discrepancy? Okay, so how good will it be? Then, in fact, if you fix some alpha with rationally independent coordinates, then the range of values is an interval. It goes between these two bounds, which involves the subnorm of alpha. So it goes between these two bounds. So let's look at them. Alpha is smaller than 1, so it can go until 1 plus d minus 2, so until d minus 1. Well, that's not super cool. But the smallest possible value is obtained when alpha, so the sum of coordinates of alpha is 1, so the infinite norm has to be larger than 1 over d. So if you make the computation, you find for the smallest value 1 minus 1 over d. So it's still not 1 minus 2d minus 2. And just for people who are used to balanceness and the study of balance properties, so balanceness is in fact of comparing to the frequency, you follow orbits and you compare the number of occurrences of words of the same length. So you have nice work by Andrieux and Vivion on the balance properties of billiard words. And if you think in terms of Sturmian sequences, they are known to have one balanceness. It's not a contradiction. It's just that balanceness is related to this discrepancy, but we forget about the frequency. But I won't. It's just for people here used to balance properties. So the question will be, okay, the target bound is 1 minus 2d minus 2. For instance, d equals 3, it makes 3/4. With billiards, well, we are 1 minus 1/3, 2/3. It's not good enough. So we have to do something better. But just to give you an idea of how these estimates are obtained, I've tried to illustrate it with the same representation. So thank you for having asked the question. So what I claim is that to compute the discrepancies, just to understand the diameter of this object, starting, so if you take 1 billiard words, the starting point is important. So what I claim is that an hypercubic billiard words, you start from some initial condition, x naught, and then you make this game of this exchange of pieces. You follow the trajectory, you code, and you get an infinite word. And what I claim is that the discrepancy, which corresponds to the distance between, at time n where you are, that is to say, the distance between n alpha on the line, on the geometric line, minus where you are combinatorially with this quantity p. So this is a discrepancy. It can be reached by following orbits which are dense. So I'm just trying to see what is the largest distance to some initial condition x naught with respect to element of this projected hypercube. So what is P in fact? I should have started like that. P is the representation map of my words. So that's what I already said briefly. I represent words by integer points or by vectors, by following letters and replacing letters by words of the canonical basis. So here I replace a word by a vector which counts the number of recurrences of each of the letters in this word. Okay, so my coding, UN, is chosen, gives the value of the face, the upper face of the unit cube you will meet once you have already reached something. So at each step you have created your word, u0, un minus 1, and you want to see which value you will have, that's the dynamical system which tells you. So you have your points here in the space, you project them to get in this world, and then to get the next decision, you have to know in which of the piece you are, to know which face you will have. So what the idea I just want to convey with this slide, without entering into much details, we use denseness of orbits, and then the question is just a geometric question, knowing the initial data which defines the line that you're coding, the x0. You want to see how far you can be in this representation of your dynamical system, which is given by this projected cube. Well, that's the essence of the computations, the estimates on the discrepancy. So that's where we are for the moment. For the hypercubic case, we are not that satisfied because, well, when you make this computation, you reach something which is not as good as the famous 1 minus 2d minus 2. So maybe it's time now to go back to the literature, and in fact, instead of trying to use what we know from codings of dynamical systems, to go back to the work of Tiedemann and Niederreiter, and fortunately, Tiedemann, already in the 80s, has been able to give, but really from a totally combinatorial way, marriage hall principle, something which has nothing to do with dynamics and geometry a priori. He was able to say, okay, I can give you construct sequences making a better discrepancy than the one of the hypercubic case. He was able to reach 1 minus 1 over 2d minus 2. So with my co-authors, we have tried to see whether this kind of Sturmian miracle was here again to be found. That is to say that this construction, which really stress it, was completely combinatorial. I don't know whether Tiedemann had in mind to follow a geometry, but when you read the paper, you really see no 3D representation and no higher dimensional representation. But what we did, yes, was to try to see whether there is a dynamics behind, and we arrived to, once again, always the same philosophy, in the sense that the sequences he constructed were again codings of translations, but this time with atoms which are still polytopal in nature, but a bit more refined than just the projection of a unit cube. So that makes strange codings, but once we have the second item saying, okay, we get codings of a translation, then we have for free, okay, we get uniquely something which is minimal, uniquely ergodic, because the parameters of a translation are rationally independent. We get a pure discrete spectrum. Well, we get a lot of information on this sequence, which, by the way, was not that obvious to understand from the construction by Tiedemann. So I already stress the fact that this dynamical viewpoint is always useful to get information from a scheduling theory viewpoint when you have such kind of answers to scheduling problem. Well, in the same way we've seen that refining partitions gave information frequencies of factors, we get in a lot of information. Speaking of factors, remember that in the Sturmian case we had this kind of miracle, linear number of factors and +1 factors, configurations of a given size, and discrepancy bounded even for the factors. So here what do we have with this construction? Well, for the factor complexity we have something which is not linear, which is ordered n to the d-1. So d is the number of colors. So why do we have this? Well, in fact, people working in this kind of object or from a viewpoint like Jimmy Walton and Arco Vuzalo from cut-and project schemes know that when we code, when we take a cut-and project with polytopal window, or when we code a two-dimensional rotation with something which is too smooth for the boundaries, there is no way that we can get a linear complexity. Okay, so that's a first result. I just want to give a hint of Tiedemann construction, but I'm still not satisfied with the way I can explain it, so I apologize in advance. I will try it, and okay, I will not spend too much time. So the idea is, as in Billard case, suppose you have decided what is the beginning of your world until letter n-1. You plot it, as we've seen with the map P. We Abelianize it. We see it in the d-dimensional space. And we put at this integer point a unit cube. And you want to intersect something. So with the cubic case, hypercubic case, well, you intersect a face. Okay? And then the discrepancy is just the difference between where you are on the geometric line minus this integer point. It's just that the projection. Okay, so we can write it with introducing this parameter t and I, 1 minus x n I divided by alpha I. Okay. And then what is written is that you have this parameter t, which is such that the starting point x0 plus t, this parameter, plus n times alpha, has to enter a cube located with the data of the world until where you are, until n-1, and you had to hit some hyperplane. Okay, so the parameter t is in fact the time that you need when you are in n alpha to meet some face. In the hypercubic case, you take the first case that you can meet. So what has done Tiedemann, well, what we could reconstruct from Tiedemann's construction is that you will optimize the choice of this time, the phase that will hit, to try to reduce the discrepancy which is measured by xn. Then it introduces two parameters, c prime, and he constructs like that sequences for which the discrepancy is between minus c prime and c. Okay, so that's the best I could do for describing Tiedemann's construction. But once we have this idea, then we will find our polytopes. So how do we find our polytopes? So with this kind of construction, it's not that you start from a cube and you select points and you get infinite worlds. That's the contrary. You make a selection, you make infinite worlds, and once you have these infinite worlds, you create a dynamical systems that I have hidden in terms of the t, the parameter t, and then to get the domain of your translation, you just follow an orbit, take the closure, and that gives you the domain. That's how we find the polytopes. So just to illustrate the cases, with this construction, these are the kind of polytopes we get. So to get them, we follow the orbit, follow the constructed world with some rules given by Tiedemann. We project them, we take the closure, and then we have to prove that these are fundamental domains for translation. So we have to prove that it ties, that it's a polytopes. There is some job to do. But what I want to stress here, that the philosophy is not that the geometry captures, selects worlds. It's that we take some selection rule for the worlds that gives you the cut and project window that we have here. And then, as I said, the fact that we have n square configurations comes from the geometry which is behind. And we can have some things which are even weirder, not connected polytopes. It depends on the choice of the parameters we have. So it's not completely satisfying. That's satisfying, as I said, we know that the shifts which correspond to the codings are nice, strictly ergodic, and so on and so forth. But trying to get more information from these shapes is not that comfortable. But anyway, so that's the situation where we are. On the one hand, we have followed the track of hypercubic worlds or classical worlds. Well, the discrepancy was not super good. We follow the track of Tiedemann. The linear complexity is not super good. But in fact, does it make a sense to have all this together? So in fact, now I escape a bit the scheduling world, because frankly, when I discuss with my colleagues from scheduling and I tell them I want to have something with linear factor complexity, they say, okay, frankly, we don't care, but well, that's life. But anyway, so now in our world, which makes more sense, is to combine all these requirements on what could be a simple, regular subshift. So a subshift which is regular could be some subshift given with prescribed frequencies and having a small discrepancy. And also being regular could mean having a very small, well, a zero entropy, but it's measured by the number of factors, a very small number of atoms when you refine the partition, so linear factor complexity. And then we can ask for something multiscale, because we've seen that it exists in the Sturmian world. So we can ask, is it possible to have bounded discrepancy for letters, but also for factors? So now the question will be how to construct infinite words which have all these requirements at the same time. Is it possible? So that might seem at first view a bit artificial to combine all these requirements, but at the same time, all these requirements means being a simple dynamical system, as I said, small number of configurations, small discrepancies, so it's really a measure of regularity. So let's come back to the billiard case. Do they fulfill all this? For instance, in the billiard case, they didn't have the smallest discrepancy, but are they multiscale when you are not in the square, but in the cube? Well, they do not seem to be multiscale in the sense that, well, okay, they don't have a linear factor complexity, but also if you look at the discrepancy for factors, then it's no more finite. It's something we did with Nicolas and Antoine Julien. As soon as we go to factors of length 2, we ruin the discrepancy. So now my feeling is that to get something having bounded discrepancy for factors is something really multiscale that requires some renormalization. And just to continue with these ideas of relating all these concepts, you can also say that a simple dynamical system is a system that has few ergodic measures. So you might want to look at factors, ergodic measures. A priori, there is no relation. Counting factors is a topological notion. Ergodic measures is something which has to do with measure theory. But thanks to Michael Bosch-Nitzen, we know that the number of ergodic measures is related to the lim sup of this counting of factors divided by n. So in particular, when you have less than 3 for the lim sup of the number of factors divided by n, you have unique ergodicity. But there is something even more striking for me. It's a recent result by Kreutz and Pavlov that says that if the lim sup is smaller than 3/2, then you are the coding of a discrete, you have a discrete spectrum. You are coding a total translation. Yeah, it's sharp. It's super nice result, because you not only relate the counting with the statistics, but also it gives you spectral information. So, yeah, it's a way to justify the fact that it makes sense to relate all these notions. Factor complexity so here it doesn't say that the spectrum has to it's discrete spectrum. It's not only a true translation, but anyway, it gives you something on the spectrum. And there's also some remark that I really love. It's that if you come back to Gottschalk-Hedlund, and if you come back to the discrepancy, bounded discrepancy just means a bounded ergodic sums for some simple functions, the indicator function minus the measure. Suppose you are strictly ergodic, you have a measure, or just ergodic with a measure. So we are looking at bounded deviations for ergodic sums. But then you have Gottschalk-Hedlund, which says, okay, as soon as you have a very easy topological dynamics case by working with a subshift. So as soon as you have bounded ergodic sums, you know that the functions in your ergodic sums, so an ergodic sum, so when I say ergodic sum, I multiply, I don't divide by n. So when you have a trajectory that is measured at some weight for which the weight is bounded, then you are a co-boundary. You have for free some function so that your continuous function is equal to g minus g composed with the dynamics. Okay, so let's use this for your ergodic sum, for your function, which is indicator function of a cylinder minus its measure. Let's do that. Okay. So we take this function, ergodic indicator function of cylinder minus its measure. We get a co-boundary. F can be written like g minus g composed with the dynamics, with the shift. Raise it to the power exponential 2i pi. Well, the indicator function gives you 1, because you multiply by 2i pi. What you get for free is a continuous eigenvalue for the Koopman operator. That is to say, the co-boundary that you had for free, the G, creates you an eigenfunction. So exponential 2i pi G composed with dynamics is equal to some constant times exponential 2i pi. And if you take in terms of additive eigenvalues, you forget the 2i pi. Well, the measures, you get that the measures of your factors, as soon as you have bounded discrepancy, give you topological factors. So it's also natural to see that discrepancy has to do, bounded discrepancy has to do with spectral considerations. Okay, so we are here. We want to find sequences which have prescribed frequencies, which have linear factor complexity, which have discrepancy at a multiscale, in a multiscale way. So now I hope I convince you that a reasonable way to do that is to say, let's start from a translation and try to find a good partition. So now the vector alpha gives you the frequencies of letters. It gives you the translation we are looking at, the minimal translation, d minus 1 dimensional. And then we want to find a good partition. So we've tried polytopes. It seems not to fit well with the multiscale strategy. So how to find a good partition? By the geometry, we are a bit stopped. So let's start in the different way. Let's construct, try to construct infinite worlds that will create the domain in the same spirit as the tie-domain strategy. So we have tools at our disposal. Remember, we had the Fibonacci substitution. So that will be the strategy we'll use. We will try to find substitutions that behave well and that will create infinite worlds that stay within bounded distance to something, and we will project, take the closure, and get nice domains. So that's the strategy we will follow. Instead of representing my translations like an exchange of pieces like that, we'll try to capture better domains, and all the properties, the multiscale properties, will be hidden in the fact these domains will have fractal boundary, and it's always reminiscent to this idea that, because they will also provide Markov partitions for tauroautomorphism, the tauroautomorphism of the matrix of the substitution, and that's always this Bowen idea that to find Markov partitions you need fractal boundaries. So that's always the same idea, that we need this kind of fractal boundaries to be able to have good codings, good atoms, good partitions that allow a multiscale behavior, saying that you code rotations and you have nice discrepancy properties for factors. So the strategy, as I said, is to construct infinite worlds, then to project them, and to create, in this sense, these fractal domains. So how to do that? As I said, we can take substitutions. If we take substitutions, we're still with algebraic data. We will just be able to reach rotations which have algebraic data. But with the title of my talk, no, you know that we will use continued fractions. So instead of working with one substitution, we will create matrices. So we take a continued fraction expansion, any kind of continued fraction expansion, which creates non-negative matrices in the same way of the Gauss map creates products of matrices. So Pascal, we discussed Arnaud-Rosy algorithm, for instance, that enters totally into this framework. You start with vector alpha. You create non-negative matrices that create cones, since they are the convergence, the product of matrices created works in this direction, M1, Mn. If we consider M1, Mn applied to the positive orthon, compare it with M1, Mn plus 1 of the positive orthon, the one with n plus 1 is included in the one with n. So you create nested subcones, and the question is to have these subcones which converge to the parameter alpha. So that's the essence of continued fraction algorithm. So it's designed to create matrices, non-negative matrices. We have seen a correspondence between matrix substitutions. So with a matrix, it's not canonical, but with the data from the matrix, I take a combinatorial object, a substitution. I compose these substitutions in the so-called S-adic way, sigma 0, sigma n. I create infinite worlds. If I'm lucky, it's uniquely ergodic, minimal, blah, blah. Then I can have a subshift. And then that's my strategy to construct infinite worlds. So in terms of renormalization, we have these two dynamics, the dynamics of the infinite product of matrices, the renormalization, the multidimensional dynamics of piso-type, and then the dynamics of the translation or the shift on the set of infinite sequences you generate. So that's a recipe to construct infinite worlds, shifts that have all the nice, that are expected to have all the nice properties that we've seen. Multi-scale bounded discrepancy, linear factor complexity, and so on and so forth. Okay? So what do we expect from continued fractions in this case? So that's several times that I pronounce the word piso. Well, we expect them to converge at an exponential speed. So if you think in terms of the usual continued fractions, the distance of Qn alpha to an integers in 1 over Qn. In higher dimension, with Dirichlet's theorem, you do not expect to have something better than 1 over Qn to the 1 over d, but at least that's exponential in convergence. So the Lyapunov exponent of the continued fraction algorithm describe this almost everywhere behavior, this convergence. So the exponential convergence is given by Qn to the lambda 1 over lambda 2, which is supposed to be negative. Okay, we have exponential convergence. So that's convergence that creates sufficient hyperbolicity to yield the following situation. Each time you give me such a continued fraction algorithm, then I can replace my matrices, I can put on it a symbolic structure, I can make it symbolic, so that, with some conditions that have to be checked, you create a set of infinite product of matrices, a set of infinite sequences of substitutions. You can put a measure on this, and with respect to this measure, all the symbolic realizations that you obtain by iterating your substitutions, all these subshifts, have the nice property that were expected. They are codings of translations. Okay, so I just rephrase it. And it says the following, that as soon as you have an exponentially convergent algorithm, then you create a coding, something multiscale, bounded discrepancy for all the factors, and it's a recipe to create S-adic systems such that for every translation, well, okay, you have a nice coding. Okay, so I would have stopped here if everything would be perfect in life, because now to answer the problem from the beginning of the lecture, we now have a machinery which works quite well. But here, I just say classically exponentially convergent algorithms. So I will mention, I'm sorry because I always speak of the same problem, but I will mention the problem we are facing, is that we have tried to understand the behavior of the lambda 1 over lambda 2 with respect to the dimension. And we arrived to something which is, in fact, just numerical for the moment. Well, we hope it won't stay only numerical, which says the following, that when we have tried to compute these exponents, the Lyapunov exponents, numerically with respect to the dimension, we arrive to something quite weird, which is that at dimension 10 for Jacobi-Perron, one of the most classical algorithms, we arrived at something positive. So I'm not even trying to compute the 1 over d plus 1 over d of Dirichlet, 1 over d of 1 minus, 1 over d of Dirichlet. We arrive to something which is not even exponentially convergent. We have a change of sign of the Lyapunov exponent. So that's where we are now. I mean, with renormalization, that is to say, we have, with what came before. We could have the feeling that for the renormalization, to have something which works at multi-scale, in a multi-scale way, we need some good convergence of continued fractions, but we seem that we cannot rely on usual continued fractions. Of course, we have other strategies. It's follow a flow, and to do what Jens Markov did with Canin and Diaz Lopez, and then having efficient Poincaré sections of a flow to give a nice continued fraction algorithm. But then the sections are not completely efficient, and there is still work to use it as a handy tool. So first problem, first limitation of the method, this convergent issue to be confirmed. And just to end, as a motivation also as this symbolic representations, we had the idea to be able to get toral Markov partitions for not only toral automorphisms, but sequences of toral automorphisms, the line of work developed by Pierre Arnoux and Albie Fischer. So in the dimension where the algorithms converge well, let's say in dimension on 3 letters, dimension 2, but when we consider these objects, when we put another dynamics, which is the dynamics, positive entropy dynamics of the toral automorphisms, then we are able to play a game with these nice partitions, cutting and stacking game, which allows to make something which looks like a flow with these partitions. And our aim would be to use this flow version of these partitions, which is a 3D version of what is well known for, on the left picture, for two-dimensional lattice basis. So we would like to use this flow to be able to understand an algorithm like Brun, for instance, like a Poincaré section of a flow living in somewhere, and we don't know where it could live. But I'm going to stop here. Jayadef is already on the mic to make it work. Yeah.
Okay, so sorry. The question I had about this last slide here is there is this work of Chung and Chevalier on
exactly.
A flow on the 3-dimensional space
exactly.
of lattices, and have a cross section which is a nice looking map.
Exactly.
It's probably too much to hope that this will, or some cousin of this will give you what you want.
Anyway, I've discussed with Nicolas Chevalier. For me, he's the right person to be able to find the nice surface on which the flow would live. So in their case, they use the best approximation strategy. In the same way, Jens has a different flow, so they also rely on homogeneous dynamics. But they capture best approximations. Which are not always unimodular, like it's known for Lagarias. But anyway, that's the, with, I think Nicolas, as you saw, is a co-author, so that's my next move with him, to try to clarify this with him,
So can you explain again what do you mean by non-stationary Markov partition?
You don't apply always the same automorphism of the torus. You always have the same torus. You don't apply the same automorphism, but you apply a sequence, a two-sided sequence of maps, which goes from copies, two-sided copies, Z copies of your torus, and you change your automorphism, which corresponds to the matrices produced by a continued fraction algorithm. They are unimodular, so it makes sense to consider the corresponding automorphism. And you want to, when you are, instead of always iterating the same map, you want to code to have codings like a subshift of finite type of the orbits, but each time you change your map. It's not stationary, it's non-stationary, but what we can do is to give, with these partitions, they change for each, you have those Z copies, you have each time a different partitions, but they are related, like they are, like you would do if you would iterate the same substitution.
Thank you.
To work with coding of one map with a one-dimensional sequence, you need this piezo condition. Without everything becomes difficult. But it seems that in many cases you get a second exponent, which also becomes of the same side. In that case, would it be possible to work not with one-dimensional sequence, but with two-dimensional sequences?
I mean, with the two first Lyapunov exponents?
Yes?
Yeah.
Like a Z2 sequence?
Like what you did with Xavier Bresson, yeah. Yeah, that's an excellent idea, yeah.
Can you say what are the 8 pictures at the bottom?
Okay, so you have a rosy fractal that you lift the rosy fractal. You have 3/8. It's a Markov partition for the total automorphism of the Fibonacci matrix. Then you deform it with a flow, so that squeezes the 8 and stretches the horizontal plane. And then you see that after some stage, you have the flow. Then you can divide the red piece into 3 pieces, which correspond to the self-linearity equation of the Fibonacci equation. And then, in fact, this picture has to show that you can restack. You restack, and then you put them above them. You have some of them which are hidden, and the last one you see a little bit of red. So the idea is to say the last picture is obtained by cutting and stacking the pieces that you obtain by deforming, deforming with the flow on 2 directions, expanding, contracting the original piece, and you get another rosy fractal. And so it's a flow version, but then the discretization of this flow corresponds to what you do when you go from one, when you iterate the matrix. So then it's done with a stationary example, but you can make it non-stationary. You can change the matrix each time, having each time a different stacking and cutting and stacking process. And that's what we try to interpret as a flow version for Brun.
Okay, so I have very maybe stupid question. So the discrepancy depends on the norm.
Yes. Yeah.
So if you try to use, for instance, the L2 norm.
Yeah, for instance, Nicolas Chevalier had a paper on poursuite, and then he took the quadratic norm. And he obtained, once again, a coding of a translation with polytopes again, but with different constants. So if we want to improve, to play with the constants, you're right, we still have some space to changing the norm. For the constant, it completely depends on the norm. Yeah.
So let's sound happy.
Thank you very much.